This is the fourth video in a series covering abstract linear algebra. In the previous video, we looked at basic definitions building up to what a group is. And today we want to look at the notion of a subgroup as well as the notion of a homomorphism and an isomorphism between groups. So let's start with a subgroup. So given a group G, a subset H of G is called a subgroup, and we write this notation right here. It looks like H is less than or equal to G, but we read this as H is a subgroup of G if we understand that the setting that we're working in is having to do with groups. Okay, so anyway, it has to follow the three following conditions. So first we need closure. So in other words, for all x, y in H, x times y is in H. Really x combined with y using the group operation. That might be multiplication, composition, or addition, depending on what the group is. Next, we need the identity to be in H. And finally, we need all inverses of every element in H to be in H. So in other words, for all x in H, x inverse must be in H. Now let's notice that these are exactly all of the axioms for a group except for associativity. And in fact, we don't need associativity here because it is inherited from the structure of G in the first place. Okay, let's go through some examples and then we'll prove a really important result called the subgroup test. So our first example is the subgroup of integers given by even integers. Well, let's just check that this is closed, and we'll just talk our way through this. I urge you to write all the details down if you need to. So if we take any two even integers and add them, we still get something that's even. So I think that's pretty clear. Notice the identity is an even integer. And then finally, if we have an even integer, then the negative of that integer is still even, so we have inverses as well. So sometimes the set of even integers is denoted by 2z because it's really just the set of all integers multiplied by 2. Now, more generally, we could have the set nz, which is a subset of all integers. So this is going to be everything of the form minus 2n, minus n, 0n, 2n, and so on and so forth. So in other words, all multiples of n instead of like all multiples of 2, which is what we have here. Okay, here's another interesting example. And so here our operation is multiplication, and the large group that we're talking about is the group of non-zero complex numbers. And so that forms a group with multiplication. And so right below that, we have this group of 4 elements that we talked about in the previous video, plus minus 1, plus minus I. So that forms a group on its own, and it's also a subset of the complex number, so that makes it a subgroup. But then we could also just take plus minus 1 and observe that that will be a subgroup of this middle group. Furthermore, it's also a subgroup of the non-zero real numbers, which I could write like this. Now, this guy right here in the middle is not a subgroup of non-zero real numbers because we have the imaginary number I in there, which is not a real number. Okay, now let's look at this next one. Let's say our parent group is the integers modulo 9. So let's recall that our operation here is to do addition of the numbers between 0 and 8, and then divide by 9 and keep the remainder. And so the set containing 0, 3, and 6 bar forms a subgroup. Well, first of all, we have the identity, which is 0. We have closure. Notice 3 plus 3 will be 6. 3 plus 6 is 9, but if we take the quotient with 9 and keep the remainder, that's going to be 0. Finally, 6 plus 6 is 12. Keeping the remainder after dividing by 9 will be 3. So we have closure there. Then furthermore, 3 and 6 are inverses of each other. So that makes this set right here a subgroup of Z9. Now, let's look at this kind of basic example, which works for any group, just to take the identity element. So the singleton, the single identity element. Well, this is definitely closed. It definitely contains the identity and it contains inverses because there's no way of getting out from this set. So this is sometimes called the trivial subgroup for any group. Okay, so now let's get rid of this and we'll look at something called the subgroup test. All right, as promised, now we're going to look at the subgroup test. So notice over here in the definition, there are 3 things to check in order to check if a subset is a subgroup. This will pare that down to only 1 thing to check. And so let's say we are given a group G. So a subset H is a subgroup if and only if for all x, y in H, x, y inverse is in H. So notice there's only 1 thing to check here. It's some sort of closure, not under just the straightforward operation, but the combination of x with y inverse. Okay, good. So let's maybe get going. Let's do this forward direction. So in other words, we want to suppose that H is a subgroup of G, and this is going to go very, very quickly. So let's suppose H is a subgroup of G and X and Y are in H. Okay, but notice the fact that Y is in H tells us that Y inverse is in H. And that's by this 3rd condition over here. Every inverse of an element in H is in H. But now from here, we have 2 elements in H that we want to combine. We have this one we started with X here, and one we started with Y inverse here. So combining those 2 elements, we'll see that X, Y inverse is in H. And so that's because of this closure operation right here. Okay, so now let's go with the reverse direction. So we want to suppose that this statement is true, and then prove that H is a subgroup. Okay, so how can we do that? So we'll build these a little bit out of order. So let's take any x in H, and let's notice that we know that x times x inverse is in H. That's just maybe setting x equal to y in our condition up here. But notice that x times x inverse is the identity, so that tells us that the identity is in H. So that checks off this 2nd condition. Okay, now let's kind of do the same thing, but with a... Now let's do our condition again, except for now, the role of x will be played by E, which we know is in H, and the role of y will be played by x. So let's maybe note that here a little bit. So let's use our defining condition with x equals E and y equals x. So let's see, that's going to tell us that EX inverse is in H, but E times anything is just whatever we started with. That's the definition of the identity element, so that means X inverse is in H. So that's looking good. That means we know that inverses are in H. Now we just have to show that it's closed under the straightforward operation. And for this case, we'll take our defining condition with x equals x, and then y equals y inverse. So I'm going to put this in quotes. And we know that y inverse is in H because of the previous step. Okay, so now let's apply our condition here. That will tell us that x, y inverse is in H. But by something we showed in the previous video, y inverse is just y, so we have x times y is in H, which means we have H is closed under the operation. So those are the 3 conditions that we needed for this to be a subgroup. So that finishes the proof of this subgroup test. Okay, so now we're ready to look at the notion of a group homomorphism. So given 2 groups G and H, and a function which we'll call phi from G to H, this function is called a group homomorphism, or sometimes just a homomorphism if we know that we're working within groups. If, for all x, y in G, phi evaluated at xy is the same thing as phi of x times phi of y. The really important thing here is that over here on the left-hand side, inside the parentheses, that is an operation in G. So in other words, we're combining x and y using whatever operation is inherent to the group G. Whereas over here, the operation is in H. So here we're combining phi of x and phi of y using whatever operation is occurring in H. Okay, so let's look at some quick examples. So my first example goes from the integers to non-zero rational numbers. So over here, my operation is addition, and over here, my operation is multiplication. So in previous videos, we talked about why each of those is a group. And my homomorphism is defined by phi of m equals 3 to the m. Although you could really take any rational number here. And so, for example, phi of -2 is 1/9 because that's 3 to the -2. Okay, so let's check that this is a homomorphism real quick. Well, let's notice that phi of m plus n is equal to 3 to the m plus n. But that's the same thing as 3 to the m times 3 to the n. That's just by exponent rules that you would learn in like a pre-calculus class. But that's exactly phi of m times phi of n. And now that we see over here, we've got addition. And then over here, we've got multiplication. So here, this is a map that produces some sort of multiplicative version of the integers within the rational numbers. So here I've got two more examples. Let's call this one psi. So it goes from integers to integers, where we've got addition in both parts. And here, psi of m is equal to 7 times m. So we're multiplying by 7. Now we can check that this is also a homomorphism pretty easily. So here we have psi evaluated at m plus n, that's 7 times m plus n. But then we know something about the distributive rule that allows us to write that as 7m plus 7n, which is phi of m plus, or I should say psi of m plus psi of n. Now here we've got addition on both sides, but we still have the condition satisfied for this to be a homomorphism. Now here's another example. I'll let you guys check this on your own. To really do this properly, you need to do something with something called the division algorithm, which is not really that difficult, but it's also not in the scope of this course. So I'll call this homomorphism pi, and it goes from integers to integers mod 5. So let's recall that the operation over here is not exactly addition, but it is addition and then divide by 5 and keep the remainder. And here we have pi of m is equal to m bar. So when we put that bar over it, that means that we really just divide by 5 and keep the remainder. So for example, pi of 12 is 2 bar. That's because if we divide 12 by 5, we get a remainder of 2. So like I said, I won't check this one, but I'll let you guys check it. Before we prove some standard results about homomorphisms, I want to look at two more examples. So two more examples. The first deals with the additive group of polynomials with real coefficients. So it's not too hard to convince yourself that this is a group with addition. If you add two polynomials, you get a polynomial. 0 is very trivially a polynomial. And then finally, if you have a polynomial and just multiply the whole thing by -1, you get the additive inverse of that polynomial. So the map that I want to define, I'll call it phi. It goes from R adjoin x, this polynomial object, to R, where again, this is with addition. And it's defined by phi evaluated at this polynomial f of x is the integral from 0 to 1 of f of x dx. The integral like from a calculus class. And we can easily check that this is a homomorphism. Notice that phi of f of x plus g of x is equal to the integral from 0 to 1 of f of x plus g of x dx, which is equal to the integral from 0 to 1 of f of x dx plus the integral from 0 to 1 of g of x dx, just by the additive property of the integral, which you learn in a calculus class. And then finally, that's equal to phi evaluated at f of x plus phi evaluated at g of x, which is what is needed to show that this is a homomorphism. Now, finally, the last one is the signum homomorphism, which goes from the symmetric group, which we talked about in a previous couple of videos, and the set plus minus 1. And that takes all odd elements to -1 and all even elements to +1. So let's do a quick example of how this works. So we would take SGN of 1, 2 would go to -1. That's because 1, 2 is a single transposition. Whereas if we take SGN of the 3 cycle 1, 2, 3, well, we first need to determine how many transpositions that can be written as. and you can check that this is factored as 1, 2, 1, 3. That's exactly 2 transpositions. That's an even number, which means this is equal to 1. And we won't check that this is a homomorphism. That's actually wrapped up in some of the calculations that we did in previous videos. Okay, now that we've covered a bunch of examples, let's prove some standard results involving homomorphisms. So the first basic result we'll prove is that the composition of homomorphisms is a homomorphism. And we'll do this with the composition of 2 homomorphisms, but then iteratively applying this over and over and over, you could see that this is good for the composition of any number of homomorphisms. Okay, so let's give ourselves a setup. So let's let phi go from G to H, and maybe psi go from H to K, be homomorphisms. So under all of this is that G, H, and K are all groups. Okay, so let's maybe put this into a string so we can see which order the composition needs to go. So as a string, we have G being mapped to H being mapped to K. So notice we have psi doing this last map, we have phi doing this first map. So the composition from G to K will be something like this. We need to start with phi and follow it with psi. And we're reading from right to left. So if we were to write it down, it would read as psi composed with phi. Notice this will eat things from G and give things from K. So let's maybe note, as functions, we have psi composed with phi goes from G to K. And we want to determine if that is a homomorphism or not. Or in fact, we want to show that it is a homomorphism. Okay, so let's suppose that X and Y are in G. And then let's calculate psi composed with phi evaluated at X times Y and see if we can factor it out so that we do have a homomorphism by this definition over here. Okay, so by the definition of composition, this is psi of phi of XY. Good. But now we can work inside of psi to break that into 2 pieces using the fact that phi is a homomorphism. So this is going to be psi evaluated at phi of x, phi of y. But now we can use the fact that psi is a homomorphism to break that apart. So that's going to be psi of phi of x, psi of phi of y. But now we're essentially home free. We just have to rewrite that as psi composed with phi evaluated at x times psi composed with phi evaluated at y. That's exactly what we needed to finish this proof. Okay, so now I've got another proposition to go over. Now we're ready for our next result. So we want to start with phi, which is a homomorphism from group G to group H. And then the identity of G will be denoted by E sub G. The identity of H will be denoted by E sub H. So we have 2 things to prove. First off is that phi evaluated at the identity E sub G is equal to the identity E sub H. So phi takes the identity to the identity. Then second, that phi evaluated at x inverse is the same thing as phi of x inverse. So it takes inverses to inverses. Okay, so let's get going. Okay, so let's start with this first one. So I'll start by writing EH times phi of EG, like this. Then I'll take this phi of EG and rewrite it as follows. I'll write this as phi of EG, EG. It's because the identity times the identity is very clearly the identity. But now we can take this guy right here and split it into 2 parts using the fact that phi is a homomorphism. So we have EH, phi of EG, phi of EG. And I'm not being careful at all here with my associativity because we know that we have associativity. So that means that we could put parentheses anywhere we need to. In fact, that means we can just leave them off altogether because it's kind of understood that all different ways of grouping give us equal things. Okay, great. But now let's look at this guy right here versus this guy right here. And notice by a proposition that we had in a previous video, we can do right cancellation to cancel this rightmost term. And that will leave us with E sub h is equal to E sub h phi of E sub g. Now, we'll play a similar game. We'll take this left-hand side and multiply it by E sub h. That will have no change at all, again, because we're combining the identity with the identity. And now we can use left cancellation from a previous video to cancel this with this, and that will leave us with the desired result that E sub h is equal to phi of E sub g as needed. And now let's move on to the next one. So I'll start by writing the identity on h is the same thing as phi evaluated at the identity on g. But I'll rewrite that identity on g as x times x inverse. So I have x inverse, like that. Now I'll apply the fact that this is a homomorphism to give me phi of x times phi of x inverse, like this. And now I'll left multiply this entire equation by phi of x quantity inverse, and that'll give us the left-hand side of phi of x inverse, and then on the right-hand side, this phi of x cancels and leaves us with phi of x inverse. But that's exactly what we wanted for this second result. Now we're going to look at a couple of concepts that arise from homomorphisms that give us kind of particular subgroups of the domain and the codomain. Now we want to expand on the notion of a homomorphism to that of an isomorphism. So a bijective homomorphism is called an isomorphism. So if that isomorphism goes from G to H and is called phi, then we might say G is isomorphic to H, and we would write this here. So we've got 2 equals with a little squiggle on top. So we would read this as G is isomorphic to H. So let's look at some examples and some non-examples of isomorphisms. So let's start maybe with this bottom one. So I've called it psi. It goes from all additive real numbers to just positive multiplicative real numbers. So notice this forms a group. The identity is 1. And then all inverses are just reciprocals. But if you have positive number and take the reciprocal, it's still positive, so we're good to go there. And here, if we take psi of x to be e to the x, that is indeed an isomorphism. And that follows just from some basic calculus ideas. So in particular, we know that it is 1-to-1 because if psi of x equals psi of y, that means that e to the x equals e to the y. Taking the natural log of both sides, we see that that means that x is equal to y. And then furthermore, we know that it is onto because if we take psi of the natural log of x, we get exactly x. And we're able to take the natural log of x for anything which is a positive real number. So this is kind of allowed here. Now I've got 2 non-examples as well. The first goes from integers to non-zero rational numbers. It's the example that we saw before that takes m to 3 to the m. So this is injective, or 1-to-1, pretty much for the same reason that this is 1-to-1, but it is not surjective. So let's notice that, for instance, the number 2 will not be mapped onto. So we could write that 3 to the m is not equal to 2, and this is true for all integers m. I think that's pretty clear. So we found something that is not in the range of this function, meaning that it's not onto. Okay. Now, what about this signum map that we did before from Sn to plus minus 1? This is most definitely surjective because 1 is sent to 1 and 1, 2 is sent to -1, but it's not injective, at least for n bigger than or equal to 3. Let's notice if n is bigger than or equal to 3, then SGN of 1, 2, 1, 3 is also equal to +1. So we found 2 elements, this guy right here and the identity, that are both mapped to 1, but they are not equal. That means it's not injective. Now there are 2 special subgroups that do some sort of measurement of how far a homomorphism is from being an isomorphism, and those are the kernel and the image. So let's look at the definition of those here, and then we'll look at some examples. So given a homomorphism, phi from G to H, the kernel is going to be all elements from G that are mapped to the identity in H. So perhaps we should have an E sub H here to show that we're going to the identity in H. We could rewrite that as the inverse image under phi of the identity element. That's using this notion of an inverse image. Next, the image of phi is going to be all elements y in H such that y is equal to phi of x for some x in G. So you could also write that as phi evaluated at the whole group G. Okay, so let's get rid of this and then we'll look at some examples. So let's look at two examples where we calculate the kernel. The first is psi going from r to r bigger than 0. So this is the example that we saw before. It says psi of x is e to the x. So as before, we saw the image was everything. So let's suppose that x is in the kernel of psi, and let's notice that means psi of x is equal to the identity over here, but the identity over here is 1 because this is multiplicative. But that's the same thing as saying that e to the x is equal to 1, but e to the x equals 1 only has a single solution, and that is x equals 0. So if x is in the kernel, it must be equal to 0. That tells us that the kernel of psi is in fact equal just to the singleton 0. Now let's look at this next example. Phi goes from z to z5 and it takes m to m bar. In other words, it divides by 5 and keeps the remainder. So let's calculate the kernel in this case. So let's suppose that m is in the kernel of phi. That tells us that phi of m is equal to 0 bar in z5. But applying phi, that tells us that m bar is equal to 0 bar, which tells us that when we divide m by 5, we get a remainder of 0. But that means m must be a multiple of 5. So we might write m is equal to 5k for some integer k. Okay, but that means that we could rewrite the kernel as all multiples of 5. So that would be like 0 plus minus 5 plus minus 10 plus minus 15 dot dot dot. But that would be 5z using some notation that we had previously in the video. Okay, so we're going to finish this off by proving a couple of standard results involving the image and the kernel, and then I'll leave you with some warm-up exercises. So our first result will be to prove that the kernel of phi is a subgroup of G, and the image of phi is a subgroup of H. And we'll do this with the subgroup test. So let's maybe start with this one first. So let's suppose x and y are in the kernel of phi. And I want to point out that by the subgroup test, what we want to do is show that x, y inverse is in the kernel of phi. But let's recall what it takes to be in the kernel of phi. It means when you are evaluated by phi, you go to the identity. So this is just going to involve a pretty quick calculation. So I'll say that we'll notice the following calculation. Phi evaluated at x, y inverse is the same thing as phi evaluated at x, phi evaluated at y inverse. That's because phi is a homomorphism. But that's the same thing as phi evaluated at x, phi evaluated at y inverse. That's by something that we proved a little bit earlier in the video. But then phi of x is equal to the identity on H, and phi of y is also the identity on H. But we've got an inverse attached to that. But the identity is its own inverse, so we in fact do not need that right there. Furthermore, the identity times the identity is the identity. But the fact that we have started here, that phi evaluated at xy inverse is equal to the identity on H, is exactly the condition we need for xy inverse to be in the kernel of phi. And that finishes the proof of this first little result. Okay, so now let's move on to this second one. Again, we'll use the subgroup test. So let's suppose, maybe I'll use slightly different letters here. So maybe Z and W are in the image of phi. And just as we discussed before, we want to show that Z W inverse is in the image of phi. Okay, great. But Z and W being in the image of phi tells us that Z equals phi of X and W equals phi of Y for some, let's see, X and Y in G. That's the entry phi into being inside the image of phi. And now we can just follow our nose for a way to produce something like this as an output of phi. So let's maybe note that phi evaluated at X, Y inverse is the same thing as phi evaluated at X times phi evaluated at Y inverse using properties of homomorphisms, but that's exactly Z times W inverse. But look at what we've got. We've got Z times W inverse is the output of our homomorphism phi, but that's exactly what we need for it to be in the image. So that means ZW inverse is in the image of phi, making the image of phi a subgroup of H. Okay, great. So I've got one more thing to prove, and then we'll end with some warm-up exercises. So we're going to end with a very important and classic result. This says that phi is injective, in other words, one-to-one, if and only if the kernel of phi only contains the identity. In other words, the kernel of phi is trivial. And this is such an important result that you almost always check that phi is injective by checking that the kernel is really just the identity. So really, this almost replaces the definition of injectivity. Okay, so let's get to it. We have an if and only if statement, so that means we need to prove two directions. Let's prove this forward direction first. So let's suppose that phi is injective and X is in the kernel of phi. Okay, but let's notice that means that phi of X is equal to E of H, right? That's what it means to be in the kernel. But EH is the same thing as phi evaluated at EG. That's by a previous result that we proved today. But now we can apply injectivity to say that X is equal to EG. So just to reiterate, injectivity tells us that this X is equal to this EG. We can basically just forget about the phi there. But that's exactly what we need to prove that the kernel only contains the identity. We try to get something else in the kernel, and we end up with that kernel is really just equal to this identity element. So that's where we end this. The kernel of phi is really just this identity element. Nice. Now let's do this reverse direction. So in other words, we want to suppose the kernel of phi is equal to EG. So in other words, the kernel only contains that single element, and we want to suppose that phi of X equals phi of Y. And in order to prove injectivity, X must be equal to Y. Okay, so let's notice that we can take this equation right here and rewrite it as phi of X, phi Y inverse is equal to EH. Just right multiplying by phi Y inverse. But next, we can combine the things on this left-hand side using properties of homomorphisms to rewrite this as phi of X, Y inverse is equal to EH. But now this guy right here being mapped to the identity is exactly the condition for XY inverse to be inside of the kernel of phi. But the kernel of phi is just a singleton. That means that this XY inverse must exactly be equal to that singleton EG. But now we can right multiply by y, and we'll see that we immediately get x equals y, which is exactly what we need in order to have injectivity. So just to reiterate, we started here and we ended here, and we used this given in order to go from one side to the other. Okay, so I can't reiterate enough that this result is super, super important. You almost always want to test injectivity by looking at the kernel. Okay, so let's leave today with a couple of homework exercises. So I'm going to leave you guys with a couple of warm-up or homework type exercises. So the first is to give an example of a subset of a group which is not a subgroup. The next is to show that the map phi from Z3 to S3, which takes 0 bar to the identity permutation, 1 bar to the 3 cycle 1, 2, 3, and 2 bar to the 3 cycle 1, 3, 2 is indeed a homomorphism. Finally, we want to suppose that phi from G to H is a homomorphism, and then show that for all x in G and integers n, phi of x to the n is equal to phi of x to the n. And you're really going to want to split this into two cases, the case when n is positive and the case when n is negative. And that's a good place to stop.